Application of machine algorithms for classification and formation of the optimal plan. Abstract. Linear programming is widely used to solve problems of resource allocation, determining the highest profit or lowest cost, inventory management, the formation of an optimal transportation plan, the identification of research, and more. One of the approaches to solving problems of linear programming is the applying of the duality principle, which is methodologically related to the theory of systems of dependent inequalities. This aspect better explains the concept of duality in linear programming problems to general mathematical rigor. Introduction. Known methods of transition from a primal problem to a dual one are based on qualitative transformations and are meaningful. Formalization and proof of the correctness of the algorithm for constructing a dual problem for an arbitrary form of representation of a primal problem will make it easy to obtain correct pairs of known dual problems. The relevance of research is due to the requirements for simplification of solutions of linear programming problems based on the development of a formal algorithm for the transformation of a primal problem to a dual linear optimization problem. Setting the task determines the problem of the method of Svm for the dual problem. Compare dual Svm and primary, analyze the algorithm of the method, apply it in practice. Svm Model, a method of data analysis for classification and regression analysis using models with supervised learning with related learning algorithms called support vector machines. For a given set of training samples, each of which is marked as belonging to one or the other of the two categories, the Svm Training Algorithm builds a model that assigns new samples to one or another category, making it an incredible binary linear classifier. The Svm model is a representation of samples as points in space, reflected in such a way that samples from individual categories are separated by a clean gap that is the widest. The new samples are then mapped to the same space, and a prediction is made of their belonging to the category based on which side of the gap they fall into. Observation of the existing methods. Each linear programming problem corresponds to a dual, formed by certain rules directly from the condition of the primal problem. As a result of intensive research in the field of machine learning aimed at improving the quality of classifiers, a new generation of methods appeared. In particular, SVM, boosted decision, regularized logistic regression, neural networks, and random forests. Many of these methods, including the SVM method, have been used successfully to solve information retrieval problems, particularly in text classification. The SVM is a kind of wide gap classifier. It belongs to machine learning methods based on vector space models, the purpose of which is to find dividing surfaces between classes as far away from all points of the learning set, possibly ignoring some points as emissions or noise. If the training set contains two classes of data that allow linear division, then there are a large number of linear classifiers with which you can divide this data. It's intuitively clear that a dividing surface passing through the middle of a strip separating two classes is better than a dividing surface lying very close to instances of one or both classes. While some teaching methods such as perceptron make it possible to find at least one linear separator, other methods such as the naive Bayesian method find the best linear separator using a certain criterion. In particular, the SVM looks for a dividing surface as far away from any data points as possible. The distance between this surface and the nearest data point is called the margin. SVM necessarily implies that the decisive function is completely determined by usually a small subset of data that affects the position of the separator. These points are called support vectors, because in a vector space a point can be considered as a vector between the origin and this point. Consider a dataset of n points in the form where I equals to -1 or 1 identifies to which class the point x belongs. Each point is a p-dimensional real vector. Svm means to find the maximum hyperplane that separates groups of points belonging to y equals 1 or y equals -1. Any hyperplane can be written as a set of points x that satisfies the condition where W is a normal optional vector to the hyperplane. Parameter b divided by W determines the displacement of the hyperplane from the origin on the normal vector. Figure 1. Visual representation of SVM. Soft margin. To extend the use of SVM to cases where the data is not linearly separated, we introduce the loss function. This function is 0 if x lies on the correct side of the margin. For data lying on the wrong side, the value of the function is proportional to the distance from the margin. Thus, we need to minimize. Gamma determines the trade-off between the size of the margin and the guarantee that the point lies on the correct side of the margin. Hence, if gamma is very small, the second operand becomes insignificant, and the function will behave with a hard margin. The calculation of the soft margin classifier is to minimize the expression of the form. Primal problem. Minimization can be rewritten as a limited optimization problem with differentiated objective function as follows. For each I, we introduce a variable e. Note that e is the least positive number it satisfies. Thus, we can rewrite the optimization problem. This is called the primal or primary problem. Solving the above problem for the dual Lagrange, we obtain a simplified problem. This is called a dual problem. Since the problem of dual maximization is quadratic function c that satisfies two linear constraints, it's effectively solved by quadratic programming algorithms. The variables c are defined in such a way that it follows that W can be interpreted as a linear combination of support vectors. Offset b can be restored by finding a point on the field boundary in solving. The equation gives the optimal value of W in terms of C. Suppose we have adjusted the parameters of our model to the training set, and now we want to make a prediction for the new point x. Then we will calculate and forecast y equals 1 if and only if this value is greater than 0. But this value can also be written as. So, if we find C to make a prediction, we have to calculate a value that depends only on the internal product between x and the points in the training set. Moreover, we have previously seen that C will be equal to all but 0 for support vectors. Thus, many terms in the above sum will be 0, and we really only need to find the internal products between x and the support vectors, which are often only a small number, to calculate formula 9 and make our prediction. Considering the dual form of the optimization problem, we got a good idea of the structure of the problem, and we can write the whole algorithm in terms of only the internal products between the vectors of the input functions. This property is important to apply kernels to our classification problem. The obtained algorithm supporting vector machines will be able to effectively learn in spaces with high dimensions. Also, dual SVM requires fewer kernel estimates than the primary. Therefore, it gives a more stable result in less computational time. Table 1. Comparison between primal and dual SVMs on the different datasets. Except Hiragana 13 and Hiragana 105 datasets, dual SVM is faster, and for Hiragana 50 datasets, the number of support vectors for dual SVM is less. However, from this experiment, it can be clearly concluded that the dual SVM is better than the primary SVM in terms of stable convergence and learning speed. Dataset. The IRIS dataset was chosen for the implementation of the support vector method. This is a well-known set of data used in the area of machine learning. The dataset contains 3 classes of 50 objects, where each class refers to the type of plant. One of them is linearly separated from the other 2. The other 2 are not linearly separated, which will demonstrate different implementations of SVM. Dataset attribute information. Sepal length in centimeters. Sepal width in centimeters. Petal length in centimeters. Petal width in centimeters. Classes: Iris setosa, Iris versicolor, and Iris virginica. Visualization. The best way to analyze a large data set is to visualize it. Data visualization refers to the approaches used to understand data through visual representation. The main purpose of visualization is interpretation of a large data set into visual graphics to easily understand complex data relationships and quickly get an imagination of the data set. Figure 2 shows a histogram of the frequencies of the data set, which can be used to understand the trend of length or width of the petals for each type of plant. Figure 2. Histogram of frequencies. From Figure 2, it seems that the type of petal Virginica is much larger than the others, and sepals are mostly 2. Setosa has the smallest size and small range of values, versicolor medium in size. The box plot, Figure 3, shows the distribution of data by quartiles. The average values and the statistical emissions are highlighted. The vertical lines, tendrils, drawn to the rectangles reflect the variability of the values outside the upper and lower quartiles. Any point on these lines is considered a statistical ejection. The other two species are larger and have larger tendrils, which characterize a large scope. Figure 3, box plot. The heat map Figure 4 shows the levels of correlation between attributes and their linear dependencies. The values of the length of the sepals depend entirely on the values of its width or vice versa. In the case of a petal, the length and width are independent of each other. It's also interesting that the length of the petal depends on the length and width of the sepals. Figure 4, heat map. In Figure 5, you can see the linear separation between classes, namely that Setosa is linearly separated from versicolor and Virginica, and versicolor and Virginica are not linearly separated. It means that in the first case it's necessary to apply a Svm with a hard margin, and in the second with soft. Figure 5, scatter plot. Statistical analysis. Table 2, statistic of the iris dataset. From this statistical table it is seen that the size of the sepals mostly is larger than the size of the petal. Also, since the variance and standard deviation characterize the scattering of values around the distribution center, it can be concluded that the variation of petal size values between plant species is much larger than for the sepals. Results. 2 arbitrary points from the iris dataset are selected for analysis, and the optimal hyperplane will be calculated. Let first arbitrary point A and second B, where X index in the dataset, Y length of the sepal. The point A will be considered negative, B positive. Thus, Y for A equals 1 and Y for B equals -1. Figure 6, visualization of the selected points. The goal is to find the hyperplanes that separate these 2 points in the best way. This means that it's needed to find the hyperplanes that leave the maximum margin between the nearest points and the hyperplane, namely to find the optimal separate hyperplane. It's now also known that any hyperplane can be described as where W normal vector to the hyperplane and B divided by W perpendicular distance from the hyperplane to the origin. Support vectors are the closest points to the separating hyperplane. In this case, there are only 2 vectors that will also be support. To find W and B, dual form should be introduced. It contains a quadratic objective function with constraints. After data substitution, solving this problem by the Lagrange method of multipliers, a necessary condition for the extrema of the Lagrange function is the equality of its partial derivatives on the variables x1, x2, and y. Build system, solved system. So the Lagrange multipliers are equal to calculating normal vector and Bayes value. Returning to the representation of the hyperplane and substitute the numbers. Figure 7 shows the hyperplanes that best classifies our data, and theoretically all positive points will be on the left and negative points on the right. Dark blue color indicates the hyperplane itself. Dotted lines form a margin. Figure 7. Visualization of the hyperplane. Comparison with program result. The values of W and B are calculated manually and coincide with the result of the program, so the calculations are correct. Also, since we have only 2 points in this case, they act as support vectors, one for each class. The coefficients of these support vectors in the objective functions correspond to the Lagrange factors calculated manually. Figure 8 shows the calculated results using the program for the entire dataset. Figure 8. Visualization of the dataset. And shows the sepal lengths of two linearly separated plant species of the iris dataset, Y, which must be classified using the Svm algorithm programmatically. We see that the data are linearly separated and easy to classify. The problem is in finding the optimal solution. The result of the program. Figure 9. Visualization of the hyperplane. In Figure 9, two types of planes are classified by the hyperplane calculated programmatically. Since one of the parameters of the classification is the index, an iris dataset takes into account the indexation, namely setosa from 1 to 50, virginica from 50 to 100, and versicolor from 100 to 150, so the support vectors and their number for each class are found correctly. Planes with an index less than 75 will belong to setosa and more to versicolor, but it's necessary to remember about possible cases where the sepal length value will be considered. Conclusion. The dual method of support vectors consists in solving the Lagrange problem. Found Lagrange multipliers help to calculate the normal vector W and draw a separate hyperplane in an easy way. Solving the primary problem, it obtains the optimal W, but nothing about the Lagrange multipliers. To classify the point X, it is needed to clearly calculate the scalar product, which can be very expensive if the number of variables is large. Solving the dual problem obtained Lagrange factors where A equals 0 for all except a few points support vectors. This problem is very efficiently calculated if there are few support vectors. Also, with scalar product that includes only data vectors, it's possible to use kernel trick for nonlinear problems. Dual SVM in nonlinear problems is more stable and faster than the primary because it performs fewer kernel estimates. Lagrangian is used to determine the line that best separates our data. In the real world, most problems are not separated linearly, so kernel tree can be used to split data using something other than straight line. SVM can be successfully used to control complex electromechanical systems. It can ensure that adaptability of control algorithms performs the functions of an observer and identifier of unknown parameters. A reference model, it can be used to control complex nonlinear objects.